Hi guys, welcome to the Heart as a Pump lesson. This will be the first in a series of 4 lessons where we finally start to talk about the cardiovascular system in some depth. This won't be an overview lecture. This won't be, it won't be just sympathetic nervous system. We went through cardiac muscle, smooth muscle, sympathetic nervous system. A lot of different varieties of facts that we've put together. We've thrown a lot of different things at you that have to do with the system, their individual components, their introductory physiology things that many of which you'll apply as you go through the curriculum. This lesson, we're going to actually start to put those facts that I've given you together to describe how the function operates as a whole. And this lesson and then the 3 that come after will do that, okay? It seems like it took a long time for us to get here, but it was necessary. So, all right, first, a little review. Now, I know you haven't had the action potential in any depth yet, but we've introduced it. And so you guys know sort of what the shape is. There's a plateau on this thing. And the ion which flows and is responsible for that plateau is which of the 4? And if you want to pause here and think about it, go ahead. And now I'm going to give you the answer. It is calcium, okay? The membrane voltage goes up, and that opens voltage-gated calcium channels. Calcium flows from high concentration to low concentration into the cell. And as it does that, positive charge accumulates in the cell. So the inside of your membrane becomes positive relative to the outside, or relatively positive. And so you've got things that are pulling your voltage down, and you have this calcium that's pulling the voltage up, and the 2 come in balance, and you end up with a plateau phase. And it's the existence of these calcium channels that are responsible for that. Otherwise, if it was skeletal muscle and nerve, it would come right back down. All right. So you might say, so what? Well, as long as this membrane is depolarized, and as long as that membrane voltage is, up here and not down here at more negative values, you can't stimulate that cardiac cell again to contract. Okay. So what that means is that there is a refractory period, meaning a period of time where you cannot fire another action potential and excite the membrane again. The vast majority of the length of this cardiac action potential is called the effective refractory period, and that means that under no circumstances can that membrane be stimulated to throw an action potential of any type. Okay. Now, somewhat after that, there's a little bit of a gray area here between the lines, which we call the relative refractory period, where you can stimulate this cell and you can get kind of an action potential. It's kind of a weak little thing. It's not a full action potential, but you might get a depolarization of the membrane that might open up some channels. Okay. So we call this the relative refractory period, okay? So the fact that this is long increases that refractory period quite a lot, and when we get around to talking about arrhythmias, you're going to find out that that's pretty important. Okay. The other thing, physiologically, to note here is that there is no such thing as tetanus of cardiac muscle. With skeletal muscle, because this voltage comes right back down, the refractory period is really, really short, meaning that you can stimulate this cell again before it ever has a chance to relax. So what you do is you keep stimulating the cell, and the force just keeps building up and up and up and up and up, and you never get a relaxation of the cell. That's called tetanus. We'll talk about it more when we talk about skeletal muscle. It's important for you to realize that that does not happen in cardiac muscle, because as long as this membrane voltage is high, you can't stimulate this membrane again. And you can see that this cell is most of the way contracted by the time you can. Certainly it's most of the way contracted by the time you can give it a full stimulation. So because of that, you can't tetanize cardiac muscle, and nor would you want to. Under no circumstances would you want your ventricle to contract and not be able to relax. So tetanus in a ventricular muscle would be disastrous. So you can think of this as a safety factor in that respect. Okay? So that action potential propagates around the heart, and as it propagates, you guys know, it generates the signal that you get in an EKG, and at some point you will be walked through this in a lot more detail. But you guys know the deal. So it propagates through the heart, and it causes contraction. And it causes that cardiac muscle to contract like so. The action potential is propagating down the sarcolemma. Remember, it propagates from cell to cell because of the gap junctions on either end. So the action potential is firing in my sister on this end, and it reaches the end of her cell, it hits the gap junctions, and now I'm depolarized, and the action potential propagates across me from left to right, where where it propagates across the intercalated disc on my right, and I stimulate my brother. So that action potential propagates through the cell, down the sarcolemma, and down into the T-tubules, which you will note are just an extension of the sarcolemma or the cell membrane down into the cell. What is in here is effectively extracellular space, okay? And certainly the composition is at rest is pretty much extracellular space. Okay, pretty much. So we have our action potential propagates down, and it opens L-type calcium channels. These are voltage-dependent calcium channels. The voltage goes up, calcium channel opens, calcium flows across the membrane into the cytosol. That calcium accumulates in the cytosol, and it also binds to our ryanodine receptors, or our SR calcium release channels in the SR membrane. In this junctional cleft here, calcium is released from the sarcoplasmic reticulum, also out into the cytosol. So we have calcium accumulating in the cytosol from release, and from the calcium coming across through these voltage-dependent channels. And that calcium binds to troponin C, and that causes our myofilaments to contract in our sliding myofilament mechanism, okay? And we get contraction of the cell, all right? Now, there are three things that alter the way that that cell contracts, all right? One is length. And this graph shows you, if you look at our control muscle, you increase the length of the muscle before you stimulate it, okay? And so you increase that length, and then you stimulate it, you generate a certain amount of force on our y-axis. And you can see in our control, force goes up with the muscle length. So the more I stretch that muscle before I stimulate it, the more force is developed. And this is our length tension curve in cardiac muscle. And you'll recall that unlike skeletal muscle, there isn't much of a decline here. You literally can't stretch the muscle out too far beyond this point without breaking it. All right? So this is our classic increase in force with increased muscle length, and it is due to what they call the Frank-Starling effect. This has been known for many, many years, more than a century, but believe it or not, nobody is entirely sure why it happens. Some people claim, one hypothesis is that when you stretch the muscle out, it squeezes the muscle down so the width kind of gets less, and as the width gets less, you move the myosin and the actin closer together. So some people think that that might increase the force of contraction. Some people think there's an increase in the sensitivity of troponin C for calcium at different muscle lengths. Could be a combination of these things, could be something different. Okay, this though is well established over many, 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 many years. It is a fact, all right? So, having established that, note that that is not the same as a change in contractility or entropic state. These are the same thing, okay? And here's what I mean by that. Just take your muscle, take it at the same length, so stretch it to a given length x, okay, and stimulate it. Here's your control muscle, and here's how much force is developed. If I take that muscle and I'm in a different contractile state, let's say I have increased my contractility by adding a positive inotropic drug, okay, then what happens is if I stretch that muscle to the very same length, I generate more force. So this is length independent increased force of contraction, okay? By the same token, if I decrease the contractility or the inotropic state at the same length, I get less force development. So this might be diseased muscle or something like that, all right? This is an indication of disease or an indication that you did something to the muscle, okay? This increase and decrease with length is normal. That happens in you and me literally on a second-by-second basis, okay? And we'll see that in a second, okay? That is why you have to distinguish between the two. So, changes in contractility are due to, well, really a variety of different factors. Most of the time, they're due to a change in calcium in the myoplasm. If I increase the amount of calcium released or the amount of calcium that comes across here or both, and I increase the calcium accumulated in the cytosol and I increase the calcium bound by troponin C, I will increase the contractility of the muscle. If I decrease the calcium, then I will decrease the contractility, okay? A change in the number of cells, or maybe you've made some cells non-functional through disease, or you've altered the function of those cells. That will cause a change in inotropic state or contractility as well. All right, these are length-independent changes, and there are a bunch of things that will change the contractility. The last thing that alters the way that this muscle contracts is afterload. In terms of the way that the heart functions, the afterload is the pressure against which the heart pumps. In terms of the muscle in isolation, it's how much load you put on the muscle. So, if I were to lift something light, which I don't have right now, let's say my shirt tail or something, if I lift it up, that's easy, okay? There isn't much load on the muscle, and my muscle has a very easy time doing that. If I have to lift something heavy, like this table, now all of a sudden, it's much harder for me to contract that muscle. I've increased the afterload on it. So that alters the way that the muscle functions. Technically speaking, I wouldn't say it decreases the force of contraction. What I would say is it decreases the extent of the contraction, okay, that you can have. The higher the afterload, or the higher the load on the muscle, the smaller the stroke volume, the smaller that the contraction of that muscle, okay? So in terms of the heart, if I increase the afterload, let's say if I have high blood pressure, then that's going to decrease my stroke volume, because my stroke volume is dependent upon how much the heart muscle contracts. Decreased contraction of the heart muscle, decreased ejection of blood, because you have a decreased stroke volume, decreased cardiac output, decreased mean arterial pressure. Okay? All right. So these are the three things which alter the cardiac muscle function, the way that it contracts. The most frequent question I get is, how do I know if it's a change in contractility or not? The answer to that, very simply, and I think most students accept this and get it, it's easy to understand what a change in afterload is. Things like blood pressure, the force against which the heart contracts. You can tell what length is. That's easy to tell, okay? If I change the length of the muscle, I've changed the force. Anything that isn't 1 and 3, that's a change in contractility, okay? Okay. And I'll come back to that. Afterload in the heart is limited by what is known as homeometric autoregulation, and I will return to this later. If I increase the afterload and I decrease the stroke volume, then that means I've ejected less blood from the heart, which means I have more left over. Which, another way of saying that is I have increased end systolic volume. I have more blood left over because my stroke volume fell. If I have more blood left over, then that means when I fill again, I'm going to end up filling the heart more because I started with more, I fill it more. So that means I get an increased end diastolic volume. If I have an increased end diastolic volume, that means I'm stretching the muscle in the walls of the ventricle more because that heart is holding more volume and I've stretched it out to a higher volume. I have more stretch of my muscle fibers, and that means that I will increase the force of contraction of those muscle fibers, which means I'm going to increase the stroke volume back up again. So afterload always has, in a normal human being, a qualitative effect on stroke volume, but because of this homeometric autoregulation, the effect is relatively minor because every time I increase the afterload, I increase the stretch on the muscle by increasing the end diastolic volume, and the stroke volume comes back up. All right? So don't get me wrong, there's an effect. It's just not very big. Okay? And ultimately, the force of contraction depends on changes in either intracellular calcium or the response of myofilaments to that calcium. I think that makes sense to you. Calcium is necessary for contraction. The more calcium you have, the more contraction you get, or the more troponin C binds calcium, the more contraction you get, or the more fibers you have, which means more troponin C, more contraction. Okay? All right, that's the end of my spiel for this video. Thank you for your attention, and we'll move on to the next video in this lesson when you're ready.